Hello, for week 7A, I'm a little bit down right now, so didn't want to show the face, but we're going to be doing question 7 here first. This is the one I chose. You were installing a new spark plug in your car, and the manual specifies that it had to be tightened to a torque that has a magnitude of 10 newtons per meter. Using the data in the figure, determine the magnitude F of the force that you must exert on the wrench. So, in this situation, um, you want to obviously draw this out. So we have the man's hand, and he has the wrench in his hand. Boosh, boosh. That looks more like a bone, I'm gonna be honest, but you know, what can we do about it? I'm not an artist up in these parts. We have a 50-degree angle right here. 50 degrees. Um, with the force going this way, normal force going this way, and a height of 0.28 meters, and oops, that says 5. And for this specific question, we're going to be using the torque equation. So the torque equation is going to be T equals R F sine of the angle. And you know, let's just list out what was given to us in the beginning. And what was given was obviously the torque, which is 10, has a SI unit of nanometers, newtons per meter. The chemistry's messing with my head. Newtons per meter. And then we have the length, which is R, which is going to equal 0.28, then an SI unit of meters. And we were given the angle, which is an SI unit of degrees, 50.0 degrees. And what we're trying to find is the force in this situation, which has an SI unit of newtons, but for now we don't know what it is. So using this torque equation right here, we're going to rewrite it to a situation where we can solve for F, and in that situation it would be F is equal to the torque over R sine of the angle. And from here we can just plug in. So F is equal to 10, which is the torque, 10 newtons per meter, over R, 0.28 meters, times sine of the angle, which is 50. And this comes out to be F equals 10 over 0.2145, and that ultimately equals 46.6 newtons. And this is going to be the force right here in the SI units, newtons. That was question 7. Now we're going to go to question 11. The figure shows a person whose weight is W equals 738 newtons doing push-ups. Find the normal force exerted by the floor on each hand and each foot, assuming that the person holds this position. So, we just draw a new one here, and we put the person. So, those are his feet, his arms, and his leg. I mean, this is going to be his head. Sorry. And we have the center of gravity here. It's going to be down here, and it's going to go to the right 0.410 meters, and to the left, didn't mean to chop off his legs, but in that area, 0.840 meters. Yes. And in this situation, it's asking us for each hand and each foot. So, and it gives us the entire weight. So what we know here is that both of the hands and the feet are going to ultimately equal the number that was given to us in the weight. So it would be 2F plus 2. Oops. So 2 force of the hands, 2 times the force of the feet is equal to 738, because that is his final weight. And newtons, we put newtons here. This is what we're ultimately going for because we know that both of these are going to equal 738. So first we want to use a sum of torques. T equals 0. Because the person is balanced and there's no rotation, the sum of torques ultimately equals 0. So what we can do here is we can find out if we add these two together, the ultimate what's it called, amount of meters that he's holding. So like that he's taking up, plus, so 0.840 plus 0.410 is equal to 1.250 meters. And since we have this right here, we can use this to figure out the force of the hands if we just plug in. So it'd be 2FH, let me do capital H, is equal to 738 times 0.840, since that's the length that's away from the hands, over 1.250 meters. This is going to equal 495.94 newtons, but since there is a 2 on this, the force of the hands, we need to divide by 2 because each hand needs to be, each hand has a half of this force here, so it's going to be 247.97 newtons, and this is going to be per hand. Let's check here, 248, so it's rounded up. And these are going to be the force of the hands. We're also going to be using some of the vertical forces over here for the feet in this situation. We're going to be doing, because we figured out the overall force of both the hands, we can use that to solve for the force of the feet. So if we put 2 force of the feet, so FF, is equal to 738, which is his final force, minus the combined force of the two hands, 495.94 newtons. This would be newtons too. We can figure out that both of the feet are going to be 200 and 92.06 newtons divided by 2, since the forces of the foot over here have a 2 in front of them, but we're solving for both of the feet, we want to divide the final answer by 2. So this would come out to be 121.03 newtons, and this is for each foot. So ultimately we found we were given the Newton's force of the entirety of the person, and we used this. Well, we put that aside for now. We used the sum of torques to figure out, obviously, the meters in which both of these are combined to, and then we figured it out, and we used that to figure out the forces of the hands, and then we found both hands are 495.94 newtons, and at that point we could use a sum of vertical forces to finally get both the forces of the feet. And that'll be my two questions.